Leaving cert physics derivations. Most of these are in mechanics. Could be asked to derive any of the equations of motion, the most simple of which is obviously V equals U plus AT. That comes directly from the definition of acceleration. Acceleration is the rate of change of velocity. So if our velocity changes from U to V, the change is V minus U over a time t. Divide V minus U by t and you get the acceleration, change of velocity divided by time. Multiply both sides by t, and you rearrange that, you end up with V equals U plus AT. Very simple, 2 lines of algebra. The others are more subtle and take a bit of practice to make sure that you can remember the key steps. If s is equal to ut plus a half at squared, we're looking for that. We know that with constant acceleration, the average velocity in any motion will be initial plus final velocities over 2, u plus v over 2. And we know that the total displacement for any motion will be average velocity multiplied by time. That's just an adaptation of distance is speed by time. So if we say displacement s is average velocity u plus v over 2 by t, and then we sub in v equals u plus at, or we replace v with u plus at. U plus u is 2u. We multiply that out, so it's 2u by t over 2 and at squared over 2. And 2 over 2 cancels itself out, so we're left with s is equal to ut plus a half at squared. V squared equals u squared plus 2as. To get to that one, we take the equation v equals u plus at and we square both sides. So treat u plus at as a bracket like you might often have done with an algebra problem in maths. U plus at by u plus at gives you on the right hand side u squared plus 2u at plus a squared t squared. And then you factorize. You take 2a out of these two terms here. So that leaves you 2a by ut, would bring you back to 2uat. And 2 by a half is 1. A by at squared would bring you back to the a squared t squared. Now, why would you take the 2 out when there is no 2 here, forcing you to put in this half? Because that bracket very neatly now can be replaced by s, leaving you with v squared equals u squared plus 2as. This isn't officially listed as a derivation, but it's been asked as one, and I think to learn it, to be familiar with it, it's equivalent to learning a derivation. Where does the equation F equals ma come from? So Newton's second law tells us that a force is proportional to the rate of change of momentum divided by time. Momentum is mass by velocity, so a change in momentum is mv minus mu. Final momentum minus initial momentum divided by time. You can factorize there, taking m out of both of these expressions. M by v, m by u, so you can separate the v minus u out. And v minus u over t is, of course, acceleration. So now you've got F is proportional to mass by acceleration. F is proportional to ma. Whenever two measurements are proportional, they can be replaced, or you can rewrite that as F is equal to a constant times ma. And that constant could have many values depending on which units you use, but we have chosen to take the value of 1 Newton as the value you will get when 1 meter per second squared is the acceleration of an object of mass 1 kilogram. So in other words, we're letting k is equal to 1, and we take 1 Newton to be whatever then that works out to be from the equation F equals ma. From circular motion, you might be asked to derive the equation v equals r omega. Linear velocity is radius by angular velocity. From your tables in the maths section, you'll know that velocity is the length of any arc divided by time. That's just distance over time, essentially. You will know from your tables as well that L is equal to r times theta. The length of an arc is the radius multiplied by the angle subtended. That would have to be measured in radians to be written in this way, but then you can take the theta over t out, and that, of course, is your angular velocity. So v equals r omega. Comes from essentially a variation on speed is distance over time in 2 lines. The formula for acceleration caused by gravity, g, small g, is equal to g m over d squared, capital G, m over d squared. This comes from a mix of Newton and Galileo. Galileo had intuited this equation. He'd figured it out from, or equivalent, that g is determined only by your distance from the Earth, not by the mass of the object itself. And whereas Galileo had done that experimentally, Newton did it mathematically. So the weight of any object as a force must obey both Newton's gravitational law and Newton's second law. From Newton's second law, we can say F equals ma. So the weight of any object is its mass multiplied by the acceleration caused by gravity. And that, of course, its weight is a force created by gravity. So it's G by m1 by m2, capital M for mass of Earth, small m for the mass of the object over d squared. And these two equations can't contradict each other. They're both describing exactly the same thing, so they must agree with each other. We can therefore put them equal to each other and divide across by m. So small g, the acceleration caused by gravity, is equal to g m over d squared. Applies on any planet, not just the Earth. And crucially, it means that the acceleration caused by gravity is independent of the mass of an object falling. Famously demonstrated by Galileo at the Leaning Tower of Pisa in the 1600s. Satellite motion. The velocity of a satellite is g by the mass of the object it's in orbit around divided by the radius of its motion. Now, if anything is in orbit, we know we can describe its motion from the gravitational law. It's gravitation that keeps it in orbit, g by m1 m2 over d squared. And we also know it's traveling in a circle or something very close to a circle, so we can say F is mv squared over r. If we use capital M for the mass at the center, let's say the Earth, small m for the mass of your satellite, or for the radius of the motion, we can adapt the equations like that and put them equal to each other. They're both describing the same thing, so they must agree. And again, we can divide both sides by m, and here we can multiply both sides by r, giving you v squared is equal to gm over r. Similarly, for the period of a satellite, the equation t squared is equal to 4 pi squared r cubed over gm. You can say that an object in orbit must obey the gravitational law, and it must also obey the rules of centripetal force. So the force on it would be mr omega squared. And again, those two must be equal to each other. So you can put them equal to each other and divide across by m, divide both sides by r. It gives you omega squared is equal to gm over r cubed. And omega, angular velocity, follows the formula 2 pi over t. T is 2 pi over omega is the way that's represented in the tables. So the omega is squared, so that's 4 pi squared over t squared, and you can rearrange that to give you t squared is equal to 4 pi squared r cubed over gm, which famously was Kepler's law. Again, he had derived that by observing the planets. Newton derived it mathematically. The two agreed with each other. Again, it's not listed specifically as a derivation, but learning it is equivalent piece of work, I think. Does a spring follow simple harmonic motion? Well, if it's a spring, it must follow Hooke's law. For the restoring force in the spring is proportional to the displacement. F is equal to minus Ks. You can say that the weight on the end of a spring is a force acting on it, so F can be replaced by ma. We can divide both sides by m. So A is equal to minus K over m times S. And K and M are, of course, both constants. So that means that acceleration is proportional to the displacement from a fixed point. And that is the rule for simple harmonic motion. So if a spring is following Hooke's law, and if it's a spring it must, then it is also demonstrating simple harmonic motion when it moves. Resistors in series. What is the total resistance of a set of resistors in series? Here shown for 3, but the same method can be extended to many. You can say that the total potential drop across 3 resistors is the potential drop across here, V1, the potential drop here, V2, the potential drop there, V3. You add them all together to get the total potential drop. It's the same current running through each of them. So if you replace V with IR following Ohm's law, it's the total resistance, it's R1, R2, R3, but it is only one value of I because it is the same current moving through each of them, there is no place else for the current to go, and then you can divide by I. So the total resistance is R1 plus R2 plus R3, plus R4 plus R5, and so on. It applies to however many resistors are in series. If resistors are in parallel, well, then the current must split to go through the three of them. So we can say, again, taking 3 as an example, that the total current is I1 plus I2 plus I3. The total potential drop from this point here to that point there across the resistors will be equal regardless of what path is followed. So we can say, replacing I with V over R, that V over RT is V over R1 plus V over R2 and so on, and divide across by V. It'll be the same value of V, even though it's different values of R, giving you the formula for resistors in parallel. The force on a charge moving through a magnetic field. You can take as a starting point that the force on a current in a magnetic field is F equals BIL. B is magnetic flux density, I is current, and L is the length, as represented in your diagram there. But to adapt that to a single charge, let's say, for example, a proton moving into a magnetic field. So we've got a magnetic field between north and south and traveling with velocity V. So we can say that applying that, magnetic flux density is still B. The current is charge divided by time. That's follows on from the definition of 1 coulomb. And the length or the distance it travels in a fixed period of time is velocity by multiplied by time, Vt. So we can just then divide T by T. Simplify the equation, it gives you BQV. And finally, the derivation of the formula n lambda is equal to d sine theta. There are a few shortcuts taken in this derivation. To do the whole thing is several pages long. So if you're very alert to detail, you might feel that some of this isn't fully argued out. You are right if you think that. But this version is all correct. And though it skips across a few points, it's valid and has always been satisfactory for the leaving cert. So if you have light passing through a diffraction grating through several slits here, and if these light rays, they're almost parallel, but at some point over here, they will meet up and create constructive interference. If that is the case, the path difference must be a fixed number of wavelengths. So for example, one wavelength is the extra distance traveled by this light wave over this one. So if we take the triangle that's created here and redraw it over there, D is the distance between the slits. Measure the angle in here is theta, and this must be 1 or 2 or 3 or 4. It must be a whole number of wavelengths n lambda, where n must be a whole number. So the sine of theta is n lambda over D. Multiply across to get n lambda is equal to d sine theta. Those are the derivations that you are expected to know for your leaving cert. If the item comes up, they're usually worth 9 or 12 marks, which can vary from like 3 up to 4%.